So hello everybody, welcome to this lecture on linear algebra. Here we will be learning what are vector spaces, what are subspaces, the necessary and sufficient condition to identify a subspace of a vector space, and also a few problems. So what is a vector space? Let f plus dot, that is, these are the two operations, addition and multiplication. On f it's a field and elements of f are called scalars. V is a non-empty set whose elements are vectors. Then V is a vector space over F if V has two compositions, addition and scalar multiplication, such that there are some properties A into alpha plus beta equal to A alpha plus A beta for all alpha beta belonging to V, A belonging to F. A plus B alpha is A alpha plus B alpha for all AB belonging to F, alpha belonging to V. AB alpha is A into B alpha, that is it is associative for all AB belonging to F, alpha belonging to V, and 1 into alpha is alpha for all alpha belonging to V. So 1 is the unity element in F. So basically we need a unity element, then associative property has to be satisfied and the property of distributive property. So if F is the set of real numbers, we say that V is a real vector space. If F is the set of rational numbers, we say V is a rational vector space. And if F is the set of complex numbers, we say V is a complex vector space. Now V is an abelian group if alpha plus beta belong to V for all alpha beta belonging to V, that is the addition belongs to V. Alpha plus beta is beta plus alpha for all alpha beta belonging to V, that means it is commutative. Alpha plus beta plus gamma is alpha plus beta plus gamma for all alpha beta gamma belonging to V, that means it is associative. And there exists 0 belonging to V such that 0 plus alpha is alpha equal to alpha plus 0 for all alpha belonging to V. So 0 is the identity vector or the 0 vector, and additive identity is unique. Then for every A belonging to V there exists minus A belonging to V such that A plus minus A equal to 0. So this is the additive inverse. Minus A is the negative vector of A, and again additive inverse of every vector is unique. Now if F is a field, then F is a vector space over itself. Every field is a vector space over itself. C is a vector space over R. But R is not a vector space over C, because if I take 2 belongs to R and I belongs to C, 2I does not belong to R. So for it to be a vector space, it has to be a subset. A is a vector space over B if B is a subset of A. Now let V be the set of all pairs xy of real numbers, and F is the field of real numbers, and define x1 y1 plus x2 y2 is x1 plus x2 comma 0. So the y coordinate is 0, cxy is cx0. So this is a question, is V a vector space over F? So we assume that x0 y0 is the identity element of this vector space. In that case, if you add the identity element to any element, you should get the same element. So xy plus x0 y0 will be xy. But this will be x plus x0 comma 0, because that is how it is defined. The y coordinate has to be 0, will be xy. That means y equal to 0, but this is a contradiction because it need not hold if y not equal to 0. So the identity element does not exist. And what happens if the identity element does not exist? It cannot be a vector space. Now some basic properties of a vector space. Let V be a vector space over F, then A alpha equal to B alpha implies A equal to B, where AB belongs to the field and alpha belongs to the vector space. Alpha not equal to 0. So basically we are applying the cancellation property for the vector space. Elements of the vector space. Again A alpha equal to A beta implies A equal to B, where A belongs to F and alpha beta belong to V. This means alpha equal to beta, not A equal to B. So this is the cancellation property for elements of the field. Now, what is a subspace? Let V be a vector space over F and W be a subset of V. Then W is a subspace of V if W is also a vector space over F with respect to addition and scalar multiplication. So if W is a vector space satisfying the same conditions under addition and scalar multiplication, then it is a vector space. So there's an important theorem which states that a necessary and sufficient condition for a non-empty set W to be a subspace of V is that if AB belongs to F and alpha beta belong to W, then A alpha plus B beta belongs to W. So if this theorem holds, then it makes our work easier. We don't have to check all those 5 axioms of vector space. So we will prove this. We start with let W be a subspace of V. Then A belongs to F, alpha belongs to W implies A alpha belongs to W because that is a property of a subspace. It will be a vector space. Again, B belong to F, beta belong to W implies B beta belongs to W. The same logic here. So if you add both, A alpha plus B beta belongs to W because if you add two elements in a vector space, they belong to the vector space. So we have proved the first part, that if W is a subspace, then A alpha plus B beta belongs to W. What about the converse? Conversely, let A alpha plus B beta belong to W, where A, B are elements in F and alpha beta are elements in the subspace. Now we have to check the axioms one by one. If A equal to 1 and B equal to 1, alpha plus beta belongs to W. So the addition property is satisfied. W is closed under addition. If A equal to minus 1 and B is 0, then minus alpha belongs to W. So W has additive inverse. Now if A equal to 0 and B equal to 0, then 0 belongs to W. So W has an identity element. And since W is a subset of V, W is commutative and associative under addition. So if B equal to 0, so we have seen that there is an identity element, and because W is commutative and associative under addition, if B equal to 0, A alpha belongs to W. Because we have A alpha plus B beta belongs to W. So W is closed under scalar multiplication. So W is a subspace of V because it has an additive inverse, it has an identity element, it is commutative and it is closed under scalar multiplication. So we have proved that if A alpha plus B beta belongs to W, then W is a subspace of V. Now consider Rn, where n is greater than or equal to 3. These are a few examples. Let W equal to A1, A2, An belong to Rn such that A1 less than or equal to 0. The question is W a subspace of Rn? Now I am taking an example to prove that it is not a subspace. If I take minus 3, 1, 1, 1, this belongs to W because minus 3 is less than 0. But if I take alpha as minus 2 and multiply minus 2 with this vector, you get 6, 1, 1, 1, and here A1 is 6, which is not less than 0. So this does not belong to W. So W is not a subspace of Rn. Coming to the second example, again W equal to A1, A2, An such that A2 is an integer. The second coordinate is an integer. Is W a subspace of Rn? So we have 1, supposing I take an element here, 1, 1, 2, 2. The second coordinate is an integer. But if I take alpha as 1 by 3 and multiply it, you get this as 1 by 3, 1 by 3, 2 by 3 and so on. And the second coordinate 1 by 3 is not an integer. So this does not belong to W. So W is not a subspace of Rn. Coming to the third example and the last one, let W equal to A1, A2, An such that A2 plus 4A3 equal to 0. Is W a subspace of Rn? So again we are going to prove that it is a subspace here. So I take two elements A1, A2, An, B1, B2, Bn belonging to W. So this condition will be satisfied. A2 plus 4A3 is 0, B2 plus 4B3 is 0. So A alpha plus B beta will be A into A1, A2, An, that is AA1, AA2, An plus B into B1, B2, Bn. So what happens when you add it? You get AA1 plus BB1, AA2 plus BB2, AAn plus BBn. So if I take A2 plus 4A3, the second coordinate plus 4 times the third coordinate, AA2 plus BB2 plus 4 times AA3 plus BB3, I can take A common, so A into A2 plus 4A3, take B common, B into B2 plus 4B3. So this is 0 because A2 plus 4A3 and B2 plus 4B3 is 0. So A alpha plus B beta will belong to W because the second coordinate plus 4 times the third coordinate is 0. Hence W is a subspace of Rn. So we have come to the end of this class where we have learned what are vector spaces, the properties, what are subspaces, how to identify a necessary and sufficient condition for a subspace, and a few examples. Thank you.